On a clear autumn evening, if you have managed to put enough distance between yourself and the nearest city, step outside and look north. Find the constellation Cassiopeia, that irregular W of stars scrawled across the upper sky. Locate it. Then let your eyes drift just slightly downward and to the right. If the darkness is genuine and your vision has had several minutes to fully adjust, something will be there waiting for you. A pale smear, a ghostly wisp of diffuse light clinging to the blackness, so faint and so understated that most observers dismiss it without a second look. It resembles a smudge left by a careless finger on dark glass. It resembles a small cloud that has not yet decided where to go. It resembles, frankly, nothing remarkable at all. But that pale smear is not a cloud. It is not a wisp of gas. It is not a loose scattering of nearby stars, softened by distance into something indistinct. That quiet, ancient luminescence is an entire galaxy. 1 trillion individual stars burning across 200,000 light-years of space. And every photon arriving at your eye from that soft glow has been in transit since a time when the human lineage had only just begun. This is what you are actually seeing when you look at Andromeda. Not a destination, not something close. A signal from a depth of time so extreme that the entire recorded history of civilization, every empire, every war, every invention, every word ever committed to writing, fits inside the duration of its journey to your retina. A signal that departed before any creature capable of recognizing it as significant had yet evolved. And it completed its crossing tonight, quietly, while you stood under an open sky and happened to glance upward. The Andromeda galaxy holds the distinction of being the most remote object, visible to the unaided human eye. No optical aid required, no telescope, no binoculars, no instrument of any kind, just a dark enough night and a patient enough observer. It has been hanging in our sky for as long as human beings have been capable of looking up and wondering what they were seeing, and for most of that time, nobody had any idea what it actually was. The earliest surviving written record of Andromeda as a discrete object comes from the Persian astronomer Abd al-Rahman al-Sufi, who documented it in his landmark catalogue completed around 964 CE. He called it a small cloud. The description was precise, in its way. It does look like a small cloud, but al-Sufi had no conceptual framework within which to place it correctly. To him, and to every astronomer who came after him for the better part of a millennium, it was simply a smudge, among other smudges, catalogued alongside genuine gas clouds and star clusters, as though it were merely another feature of the local sky, a curiosity, a footnote, something to note and move past. Charles Messier, the meticulous French comet hunter of the 18th century, catalogued it as the 31st entry in his famous list of objects that were definitively not comets and therefore not worth his primary attention. Messier 31, he recorded it as a nuisance, an obstacle in the eyepiece, a fuzzy patch that kept fooling less experienced observers into thinking they had found something new. What Messier wanted was comets. What Andromeda represented, in his catalogue, was an inconvenience to be documented and set aside. The irony embedded in that dismissal is almost architectural in its scale. What Messier filed away as a cataloguing irritant turned out to be the single most consequential object in the history of cosmology. Not because of what Andromeda itself is, though what it is turns out to be extraordinary enough, but because of what discovering its true nature forced humanity to accept about the size and structure of everything that exists. For centuries, the dominant assumption among astronomers was that the Milky Way constituted the entirety of the cosmos. Every star, every nebula, every luminous structure in the sky was presumed to belong to one enormous system, and beyond its boundaries lay nothing but featureless, infinite dark. The spiral nebulae, those elegant pinwheel shapes that increasingly powerful telescopes were revealing in growing numbers, were generally interpreted as swirling clouds of gas within the Milky Way itself. Perhaps regions where new stars were being assembled, perhaps some other local phenomenon, but local, contained within the galaxy, part of the same structure we inhabit. Andromeda was the largest and brightest of these spiral nebulae, studied, admired, debated, but assumed to be ours. This assumption held the status of something close to doctrine, and the tension between those who accepted it and those who quietly suspected otherwise came to a formal and dramatic confrontation on the evening of the 26th of April 1920. In the Baird Auditorium of the Smithsonian Museum of Natural History in Washington, two astronomers rose before an assembled audience and argued, in earnest, about the physical scale of the universe itself. Harlow Shapley was young, ambitious, and recently elevated in reputation. He defended the established position with energy and confidence. The Milky Way, he argued, was far larger than earlier estimates had suggested, large enough that the spiral nebulae, Andromeda included, could fit comfortably within it. They were internal features, local phenomena, not independent systems. The universe was one galaxy, and that galaxy was the Milky Way, and its boundaries contained everything that existed. Heber Curtis was older, more cautious in temperament, and less willing to accept the comfortable answer. He argued the contrary. The spiral nebulae were not embedded within the Milky Way. They were autonomous structures, independent galaxies in their own right, separated from us by distances so vast that each one constituted a sovereign island of stars floating in the surrounding void. The universe, in Curtis's view, was not one galaxy. It was an ocean of galaxies, each one enormous, each one separated from its neighbors by gulfs of space that made the interior of any single galaxy look modest by comparison. The debate was not polite. The stakes were as large as stakes can be. If Shapley was correct, the universe was a single comprehensible structure, vast certainly, but singular. Humanity lived at a knowable address within a knowable cosmos. If Curtis was correct, the universe was something else entirely, something with no obvious boundary, something populated by systems like our own in every direction as far as any instrument might eventually see. Neither man possessed the evidence to settle the argument that evening. Shapley had overestimated the dimensions of the Milky Way by a significant degree, which made it easier to argue that the spiral nebulae could be contained within it. Curtis had correctly intuited the extragalactic nature of those nebulae, but his supporting evidence was suggestive rather than definitive. He had observed novae within Andromeda that appeared dramatically dimmer than novae elsewhere, implying an enormous distance. He had noticed dark structural features in the spiral nebulae that resembled the dust lanes visible in what he believed were edge-on views of other galaxies. The clues were pointing outward, but clues are not proof. The audience that night could not have known that within 5 years, a third astronomer would make an observation that would render the debate's central question permanently closed. Edwin Hubble was working with the 100-inch Hooker telescope at Mount Wilson Observatory in California, the most powerful astronomical instrument on Earth at that time. In 1925, while conducting a systematic photographic survey of Andromeda, he identified something that changed everything. Within the soft glow of the spiral nebula, he found individual stars, not just any stars. He found Cepheid variables, a class of pulsating star, whose brightness rises and falls in a cycle, whose period is mathematically linked to the star's true intrinsic luminosity. The relationship had been established years earlier by Henrietta Swan Leavitt, working at the Harvard College Observatory, through painstaking analysis of variable stars in the Magellanic Clouds. Leavitt's discovery was one of the most consequential in the history of astronomy, and it gave Hubble exactly the tool he needed. The logic was straightforward and devastating. If you know a star's true brightness, and you can measure how dim it appears from Earth, the difference between those two values tells you the distance. It is the same principle that lets you estimate how far away a streetlight is by how bright it looks. Measure the period of a Cepheid's pulsation, derive its true luminosity from Leavitt's relationship, compare that to its apparent brightness in the sky, and the distance falls out of the arithmetic. Hubble measured Andromeda's Cepheids. He worked through the numbers carefully, checking and rechecking, and the result was impossible to accommodate within the existing model of the cosmos. Andromeda was not inside the Milky Way. It was not a local feature, not a nearby gas cloud, not an internal structure of any kind. It was a completely separate galaxy, floating in the void at a distance so extreme that every map of the universe drawn before that moment was instantly and irreversibly obsolete. The universe did not end at the edges of the Milky Way. The Milky Way was one galaxy among what would turn out to be, by modern estimates, roughly 2 trillion others. And Andromeda was the first proof. In a single calculation, the known universe expanded from one galaxy to at least 2, and within a few years to millions, and eventually to the staggering population we recognize today. Every step in that expansion traced back to one smudge of light in the autumn sky that Messier had catalogued as an inconvenience and Al-Sufi had recorded as a small cloud nearly 1,000 years before Hubble trained his telescope on it. The great debate was over. Shapley was wrong about the spiral nebulae, Curtis was right, and the universe was something so much larger than either of them had been prepared to defend that the debate itself looked, in retrospect, like two people arguing about the size of a room while standing on the floor of an ocean. That discovery did more than expand the map. It permanently redefined the relationship between human beings and the scale of the cosmos. Before 1925, a serious and well-informed astronomer could stand before colleagues and argue in good faith that everything that existed fit within a single galaxy. After Hubble's measurement, that position was no longer scientifically defensible. The universe had exploded outward, not physically, but conceptually, from one galaxy to billions, from a comprehensible structure to something that required entirely new vocabulary to describe. And the object that detonated that conceptual explosion was the same faint wisp of silver light you can see on any clear autumn night without any instrument at all. Andromeda remains, a full century after Hubble's breakthrough, the most important galaxy in observational astronomy apart from our own. It is our nearest large spiral neighbor, the closest example we have of what a major galaxy looks like from the outside, something we can never directly observe for the Milky Way because we are permanently embedded within it. It is our laboratory, our mirror, and our most immediate window onto the architecture of the universe beyond our own galactic walls. But it is also something else. It is the object that more clearly than any other reveals the precise boundary between what we can see and what we can reach, between knowledge and experience, between the universe as a gallery and the universe as a territory. And to understand that boundary fully, you first need to understand what Andromeda actually is, and what the number attached to its distance actually means, not as an abstraction, not as a figure in a textbook, but as a physical reality that carries consequences so severe they fundamentally alter what the word neighbor means and what the phrase nearest galaxy tells you about the cosmos you were born into. That is where we go next. But before we do, if this kind of journey through the deep structure of reality is something that changes how you see the universe, consider hitting the like button and subscribing to this channel. It costs you nothing, and it makes an enormous difference to whether work like this can continue. Now settle in, get yourself comfortable. Let's begin. Consider what Andromeda actually is, stripped of the romantic language and the soft-focused descriptions that tend to accompany it in popular accounts. It is a barred spiral galaxy, meaning its central region is not a simple circular bulge of stars, but an elongated, bar-shaped structure from which two prominent spiral arms extend outward in graceful curves. The bar itself is composed of hundreds of millions of stars gravitationally organized into that elongated form, and the arms winding away from it are dense with star-forming regions, dust lanes, stellar clusters, and the remnants of stars that have already lived and died. From a sufficiently distant vantage point, Andromeda would appear as one of those grand, sweeping pinwheel structures that have become iconic in astronomical photography. Elegant, symmetrical, ancient, its diameter spans approximately 200,000 light-years across its visible disk. To cross it at the speed of light would require 200,000 years of continuous travel. Our own Milky Way stretches roughly 100,000 light-years across its luminous disk, though some recent measurements incorporating faint stellar populations in its outer halo suggest its full extent may reach 150,000 light-years, or perhaps somewhat more. By the most commonly cited figures, Andromeda is comparable in size to our own galaxy, possibly somewhat larger in its overall extent, though the two systems are close enough in scale that the comparison functions as a rough equivalence. Two enormous spiral galaxies of broadly similar proportions, members of the same gravitational family, separated by a gap that makes their individual sizes irrelevant to any practical question about the relationship between them. The stellar population of Andromeda is estimated at approximately 1 trillion individual stars. 1 trillion. Sit with that number for a moment before moving past it. 1 trillion is not a quantity the human mind was built to process directly. It is too large for intuition and too abstract for emotion. But try this. If you were to count from 1 to 1 trillion, speaking one number per second without pause, without sleep, without stopping for any reason at all, the counting would take roughly 32,000 years. That is longer than the entire span of recorded human civilization multiplied by 5. You could not count Andromeda's stars in a human lifetime. You could not count them in 1,000 human lifetimes. The number belongs to a different scale than anything biology has prepared us to handle. Among those trillion stars are millions of stellar nurseries, regions where clouds of gas and dust are collapsing under gravity into new suns. There are ancient globular clusters, dense spherical swarms of hundreds of thousands of stars that formed when the universe was young, orbiting Andromeda's halo like slow satellites. There are stellar remnants, white dwarfs cooling toward darkness, neutron stars spinning in the void, the collapsed cores of stars that exhausted their fuel billions of years ago. There are almost certainly planetary systems in numbers that dwarf the total count of human beings who have ever lived. Worlds with surfaces, worlds with atmospheres, worlds with water in some phase or another, arranged in orbital configurations we have not yet imagined, around suns we have not yet named. And at the center of all of it sits a supermassive black hole. Andromeda's central black hole, designated M31, carries a mass estimated at somewhere between 100 million and 200 million times the mass of our own Sunday. To put that in perspective, the supermassive black hole at the center of our own Milky Way, known as Sagittarius A, has a mass of approximately 4 million solar masses. It is an enormous object by any terrestrial standard, a gravitational engine so powerful that it bends space-time across vast distances. But Andromeda's central black hole outweighs ours by a factor of roughly 25 to 50. It is not merely larger. It belongs to a different category of gravitational object entirely, one whose influence on the surrounding stellar environment is proportionally more severe and whose history of growth through the consumption of gas, dust, and entire stars has been more dramatic than anything at the heart of our own galaxy. Andromeda is not simply large. It is the dominant member of our local group, the gravitational family of roughly 100 known galaxies, to which both the Milky Way and Andromeda belong, along with dozens of smaller dwarf systems scattered through the surrounding volume of space. By mass and by stellar population, Andromeda leads. It is the heaviest, the most luminous, and the most structurally complex member of our cosmic neighborhood. And our cosmic neighborhood, in the context of everything that follows, is the only portion of the universe we will ever have any meaningful relationship with. In January of 2025, the Hubble Space Telescope completed what its operators described as the most ambitious photographic undertaking in the observatory's history. The project, known as the Panchromatic Hubble Andromeda Treasury Program and its southern extension, had been accumulating data across more than a decade of observation, combining over 600 overlapping individual pointings of the telescope into a single continuous mosaic of the entire Andromeda disk. The final image contains approximately 2 billion pixels. It resolved more than 200 million individual stars across Andromeda's face, 200 million distinct points of light, each one a nuclear furnace burning through hydrogen at temperatures measured in millions of degrees, each one individually identified and catalogued by the telescope's instruments, each one separated from the detector collecting its light by 2.5 million light-years of intergalactic void. And that 200 million represents only the brightest fraction of Andromeda's stellar population. Hubble's sensitivity at those distances allows it to detect stars somewhat more luminous than our own sun. The hundreds of billions of dimmer stars, the red dwarfs that constitute the overwhelming majority of any galaxy's stellar census, the faint stellar remnants, the brown dwarfs hovering just below the threshold of nuclear ignition, all of them fall below the instrument's detection limit at this distance. The most detailed portrait ever assembled of Andromeda captures perhaps one star in every several thousand that actually exists within it. And yet the detail visible in that portrait is extraordinary. Astronomers can distinguish stellar types across the entire disk, identifying populations of young blue stars still blazing with the energy of recent formation, intermediate age populations in various stages of their evolutionary cycles, and ancient red stars that formed when the universe was still in its early chapters. They can trace dust lanes threading between the spiral arms like dark rivers. They can identify embedded star clusters, hundreds of them, scattered through the disk at various ages and stages of dispersal. They can read, through the distribution and chemical composition of these stellar populations, the broad outline of Andromeda's history, including a major merger event approximately 2 billion years ago with another galaxy of significant mass, a collision that reshaped Andromeda's structure and triggered waves of accelerated star formation whose signatures remain visible today in the distribution of younger stellar populations across the disk. We know Andromeda in extraordinary detail. We know its rotation rate and what that rotation implies about the distribution of mass throughout its structure, including the invisible dark matter that constitutes the majority of its total mass. We know its chemical history through spectroscopic analysis of its stellar populations. We know the architecture of its spiral arms and the substructure embedded within them. We know the orbital behavior of its globular cluster system. We know its merger history better than we know the deep history of many regions of our own planet's surface. Andromeda is, in every measurable scientific sense, one of the most thoroughly understood objects in the sky. And this is precisely where the language used to describe it begins to betray the reality it is supposed to represent. Nearest major galaxy. Our closest large spiral neighbor. The galaxy next door. These phrases appear so consistently in textbooks, in documentary narration, in press releases accompanying new images, that they have acquired the status of simple factual description. And they are factually correct, in the narrowest possible sense. Andromeda is the nearest major galaxy. There is no closer large spiral. The next comparable targets, galaxies like Centaurus A or Messier 81, sit roughly 12 to 14 million light-years away, 5 to 6 times farther than Andromeda. In the catalogue of major galaxies, Andromeda genuinely occupies the position closest to us. But nearest does not mean near. This distinction, so simple it almost sounds trivial, contains the entire architecture of what this story is actually about. When the human brain encounters the word nearest, it does not process it as a pure relative term stripped of all implication about absolute distance. It files it into a category alongside other words that carry connotations of proximity: nearest exit, nearest hospital, nearest star. The word nearest implies that whatever it describes is within some range that effort and time could plausibly overcome. Your nearest neighbor is across the street. The nearest town is down the road. Even the nearest country is, at worst, a long flight away. Nearest, in the context of human experience, means reachable. And when that word is applied to Andromeda, the brain performs a quiet, invisible, and completely incorrect translation. It hears nearest galaxy, and it understands close galaxy, accessible galaxy, a galaxy separated from us by a distance that belongs to the same basic category as other large distances we are already familiar with, just scaled up somewhat. That translation is the lie at the center of everything. The distance to Andromeda is approximately 2.5 million light-years. That figure comes from multiple independent measurement methods that converge on the same result with reasonable consistency. Cepheid variable measurements place it at approximately 2.51 million light-years. Eclipsing binary star measurements arrive at roughly 2.52 million light-years. The tip of the red giant branch method gives approximately 2.56 million light-years. Infrared surface brightness fluctuation techniques yield around 2.57 million light-years. The current scientific consensus, weighted across these methods, settles at approximately 2.54 million light-years, with an uncertainty of roughly 110,000 light-years in either direction. For purposes of this account, and in alignment with the standard figures used by NASA and ESA in their public communications, we will work with the rounded value of 2.5 million light-years. 2.5 million light-years. Said quickly, the number sounds almost manageable. You have encountered larger figures. National budgets run into trillions. The human body contains 37 trillion cells. The estimated number of grains of sand on all of Earth's beaches is several quintillion. Against those quantities, 2.5 million sounds almost modest. But a light year is not $1, and it is not a grain of sand. A light year is the distance light covers in a full year of continuous travel, moving at 186,000 miles per second. In a single year, a photon crosses approximately 5.9 trillion miles. 1 light year is nearly 6 trillion miles. That number is already a kind of violence against ordinary intuition, but you can still hold it, barely, as a very large distance made of familiar units. Now multiply it by 2.5 million. The distance to Andromeda is approximately 14.5 quintillion miles. Written in full, that figure looks like this: 14,700,000 billion miles. The number has stopped being a quantity and become a kind of argument, a formal demonstration that certain things cannot be made to feel real through arithmetic alone. This is where the translation from number to reality has to happen through a different method entirely. Not multiplication, not unit conversion. Something more like a controlled demolition of the intuition that the word nearest implies anything about accessibility. And that demolition requires a ladder. A ladder built from distances you already know, starting with the ones close enough to feel almost touchable, and climbing rung by rung toward Andromeda, watching what happens to each familiar distance as the next one arrives and renders it negligible, because that is what the ladder does. Every rung you climb makes the one below it look like a rounding error, and by the time you reach the top, the word nearest has been emptied of every implication it carried when you first heard it applied to a galaxy 2.5 million light-years away. That ladder is where we go next. Before we climb toward Andromeda, we need to establish where we are standing. Not on Earth in any geographical sense, not in the solar system in the way a textbook diagram presents it, with planets arranged in neat concentric rings around a central star. We need to stand somewhere more specific than that. We need to stand at the edge of what is known and familiar, at the boundary between distances the human mind can still process through analogy, and distances that require something else entirely. We need to feel the ground beneath our feet before we start climbing, because the ground is going to disappear faster than you expect. Start with the moon. The average distance from the surface of the Earth to the surface of the moon is approximately 239,000 miles. A beam of light covers that gap in roughly 1.3 seconds. If you stood on the moon and shone a flashlight toward Earth, someone watching from a rooftop would see it arrive before they had finished drawing a single breath. Human beings have physically crossed that distance 6 times. 12 individuals have walked on the lunar surface, kicked its grey dust, driven electric vehicles across its plains, and returned safely to Earth. The moon is the one celestial body beyond our atmosphere that humanity has actually touched. It is close enough that the Apollo spacecraft of the late 1960s and early 1970s covered the distance in approximately 3 days of powered flight, using rocket technology that, by the standards of what comes later in this story, is barely distinguishable from standing still. The moon is close. Hold on to that. It is the last distance in this story that will feel that way. Now move outward to the Sunday. The average distance from Earth to our star is approximately 93 million miles. Light covers that gap in about 8 minutes and 20 seconds. If the sun were suddenly switched off, you would not know for over 8 minutes. You would be sitting in what felt like a normal morning, the sky still bright with existing photons, and the star responsible for all of it would already be gone. At highway driving speed, the trip to the Sun would consume roughly 170 years. No human being has come anywhere near it. The closest approach any human-made object has achieved was accomplished by the Parker Solar Probe, which in December of 2024 swooped to within approximately 3.8 million miles of the solar surface during a planned close flyby. At its nearest point in that approach, the probe was moving at roughly 430,000 miles per hour. That is fast enough to travel from the surface of the Earth to the Moon in about 33 minutes. It is the highest velocity any object constructed by human hands has ever reached. Remember that number, 430,000 miles per hour. We will need it shortly, and when we return to it, the context will have changed completely. Push further out. Mars, at its closest approach to Earth, sits approximately 34 million miles away. Our fastest robotic missions take roughly 7 months to complete the crossing. Jupiter, the largest planet in the solar system, lies about 365 million miles from Earth at its nearest. The Juno spacecraft, traveling at speeds exceeding 165,000 miles per hour during its orbital insertion, required 5 years to reach it. Saturn, with its rings catching sunlight at a distance of roughly 746 million miles at closest approach, took the Cassini spacecraft nearly 7 years to reach after launch. Neptune, the outermost recognized planet, orbits at an average distance of approximately 2.8 billion miles from the Sunday. Voyager 2, the only spacecraft ever to visit Neptune, launched in 1977 and arrived in 1989. 12 years of continuous flight to reach a planet still within our own solar system. These numbers grow quickly, but they are still numbers of millions and billions of miles, still quantities that, however large, belong to the same solar system we live in, the same gravitational family, the same immediate neighborhood around the same star. Everything from the Moon to Neptune fits within a volume of space that, on the scale of what follows, is essentially a single point. Now consider the edge of the solar system itself. The Oort cloud is a vast, roughly spherical shell of icy objects that marks the outermost boundary of the Sun's gravitational influence. It is not a disk like the inner solar system, but a three-dimensional halo surrounding the entire system, extending outward to an estimated distance of roughly 1 to 2 light-years from the Sun. That is somewhere between 6 and 12 trillion miles. No human probe has come remotely close to reaching it. Voyager 1, launched in 1977, and currently the most distant human-made object in existence, has been traveling continuously for nearly 50 years. It moves at approximately 38,000 miles per hour relative to the Sunday. In that half-century of uninterrupted flight, it has covered about 15 billion miles. 15 billion miles in 50 years. The outer edge of the Oort cloud is estimated to lie somewhere between 6 trillion and 12 trillion miles away. Voyager 1 has covered, in 50 years of flight, roughly 1/4% of the distance to the Oort cloud's outer boundary. Our most distant emissary, the object that has traveled further from Earth than any other thing humanity has ever built, has barely scratched the surface of our own solar system's backyard after half a century of continuous travel. Now we leave the solar system entirely and step into interstellar space, the space between stars, and this is where the ladder takes its first, genuinely brutal jump. The nearest star system to our Sun is Alpha Centauri. It is not a single star, but a triple system. 2 stars, broadly similar to our Sun, designated Alpha Centauri A and Alpha Centauri B, orbit each other in a gravitational partnership. A third companion, a small dim red dwarf called Proxima Centauri, orbits the pair at a much greater distance and holds the distinction of being the single closest individual star to our solar system. Proxima sits approximately 4.24 light-years away. The 2 larger companions are slightly farther at about 4.37 light-years. We will round and say the nearest star is roughly 4.25 light-years from Earth. 4.25 light-years. That means light itself, moving at the universal speed limit of 186,000 miles per second, requires 4 years and approximately 3 months to cross the gap between our solar system and the nearest other one. There is no shortcut. There is no alternative route. That is the hard floor of the distance. And no physical signal, no spacecraft, no information of any kind can cross it in less time than light requires. 4 years and 3 months is the minimum. It is enforced not by engineering limitations, but by the structure of space-time itself. Now translate that into the terms of our fastest machine, the Parker Solar Probe, at 430,000 miles per hour. Aimed directly at Proxima Centauri, which it is not, the probe would require approximately 6,700 years to complete the crossing. 6,700 years. That is roughly the span of time between the construction of the first known stone monuments and the present day. It encompasses the entire arc of what we call recorded history, every dynasty and republic and empire, every technological revolution from bronze casting to semiconductor fabrication, every war and every treaty and every piece of music ever written down, and the probe would still be in transit, still crossing the interstellar void between our solar system and the nearest star, with years of travel remaining. Voyager 1 at 38,000 miles per hour would need approximately 73,000 years to cover the same distance. 73,000 years ago, anatomically modern humans were spreading across Eurasia, painting the first known figurative images in caves, wearing jewelry crafted from shell and bone. The cognitive revolution that made us recognizably human in a behavioral sense was just beginning to express itself in the archaeological record. Every human event since that moment, every generation, every lifetime, every development in language and culture and technology, all of it fits inside the travel time of our slowest interstellar capable spacecraft to the nearest star. The nearest star, the best case scenario, the shortest possible journey between our solar system and any other. And it is already a distance that functionally no existing or near-term technology can cross within any time frame that preserves the identity or continuity of the civilization that launched the mission. Now step back and look at the galaxy. Our Sun sits approximately 26,000 light-years from the center of the Milky Way, embedded in one of the galaxy's outer spiral arms, a region sometimes called the Orion Arm or the local spur. The galaxy itself, measured across its luminous disk, spans roughly 100,000 light-years. Some measurements incorporating faint outer stellar populations suggest the full extent may reach 150,000 light-years or more, but the standard figure for the visible disk is 100,000 light-years. 100,000 light-years. At the speed of the Parker Solar Probe, 430,000 miles per hour, crossing the full diameter of our own galaxy, would require approximately 156 million years of continuous flight. 156 million years. That is longer than the entire span of time separating the present day from the late Jurassic period, when dinosaurs dominated every landmass on Earth and the first birds were just beginning to experiment with flight. Our fastest spacecraft, crossing our own galaxy at maximum velocity, would take a journey longer than the age of the dinosaurs to complete it. The species that built the spacecraft would almost certainly have been extinct for tens of millions of years before it arrived at the far rim. Light itself needs 100,000 years to cross the Milky Way. Everything we might build needs incomparably longer. The Milky Way contains somewhere between 200 billion and 400 billion individual stars. If you assigned each star a single grain of rice, the resulting pile would fill a concert hall from floor to ceiling several times over. All of those stars, separated from their neighbors by gaps of several light-years, each on average, distributed across a rotating disk 100,000 light-years in diameter, constitutes our home, our galaxy, the structure we will never fully cross. And the Milky Way is not a static object. It is a living machine. Our solar system orbits the galactic center at approximately 515,000 miles per hour, completing one full circuit roughly every 225 to 250 million years. In the 4.5 billion years since the Earth formed, our planet has completed approximately 18 to 20 orbits around the galactic center. When the non-avian dinosaurs went extinct 66 million years ago, Earth was a quarter of the way through its current lap. The stars visible in tonight's sky were in different positions relative to our Sunday. The constellations did not exist. The night sky was populated by strangers. Everything you see when you look up is temporary, a snapshot of a slow dance that will look entirely different in another 100 million years and will have changed beyond recognition in a billion. But this complexity, this depth of structure and motion and history, all of it belongs to the inside of one galaxy, one island, one point in the larger cosmos, and we have not yet taken the step that makes everything described so far feel like a walk around the block. The distance from the Milky Way to Andromeda is approximately 2.5 million light-years. The diameter of the Milky Way is approximately 100,000 light-years. This means the gap separating us from Andromeda is 25 times the full width of our own galaxy. 25 times. Imagine the Milky Way represented by a single football field, 100 yards from end zone to end zone. The far end zone represents the opposite edge of our galaxy, 100,000 light-years away. Now ask where Andromeda would be at that same scale. It would be 25 football fields away, not 25 yards, 25 complete fields, each one representing the entire diameter of a galaxy containing hundreds of billions of stars, laid end to end across a distance that your eye could not take in at once, even if you stood at one end and looked toward the other. Between our galaxy and Andromeda, there is almost nothing. The intergalactic medium, the diffuse material filling the space between galaxies, is among the most perfect vacuums occurring naturally in the universe. Within the Milky Way, the space between stars is already extraordinarily empty, containing roughly 1 atom per cubic centimeter of hydrogen and other trace elements. That interstellar medium sounds sparse, and it is, but it is almost crowded compared to what lies between galaxies. The intergalactic medium in the region between the Milky Way and Andromeda contains approximately 1 to 10 atoms per cubic meter, not per centimeter, per meter. That is roughly 1,000,000 times emptier than the already near-perfect vacuum between stars. For comparison, the most advanced ultra-high vacuum chambers ever constructed on Earth achieve densities of approximately 100 atoms per cubic centimeter. The space between our galaxy and Andromeda is tens of millions of times emptier than the best vacuum human technology has ever produced. It is not merely empty. It is empty in a way that makes all other emptiness look crowded. There are no stars to navigate by in that crossing, no gas clouds to mark progress, no gravitational oases where a hypothetical spacecraft might alter its course or replenish any resource, no structure of any kind that a traveler could use as a landmark or a reference point. If you were placed somewhere in the middle of that void, equidistant between the two galaxies, the Milky Way would appear as a faint smudge in one direction and Andromeda as a faint smudge in the other, and between them, in every direction, for over 1,000,000 light-years, the universe would be functionally, completely, perfectly empty, a darkness so thorough that the word darkness fails to describe it. Not the darkness of a room with the lights off, not the darkness of a rural night far from cities. Those darknesses are filled with nearby objects, with the faint glow of distant light sources, with the texture of a world still present around you, even if temporarily invisible. The darkness of the intergalactic medium is the absence of everything. No light, no matter worth speaking of, no magnetic fields of meaningful strength, no radiation pressure, no reference frame of any practical use. A void so absolute that the concept of location itself begins to feel like a fiction. This is the medium through which any crossing to Andromeda must pass. There are a handful of exceptions scattered within that void. The local group, our gravitational family, includes dozens of small dwarf galaxies distributed through the space between the Milky Way and Andromeda. The large and small Magellanic Clouds orbit our own galaxy as satellites. Andromeda maintains its own retinue of companion dwarfs. In April of 2026, astronomers confirmed the existence of a newly identified ultra-faint dwarf satellite of Andromeda, designated Andromeda XXXV, located approximately 388,000 light-years from Andromeda's center and roughly 2 million light-years from Earth. It was initially detected during a visual inspection of survey images by an amateur astronomer, a discovery that underscores both the scale of the surrounding space and how much of it remains incompletely mapped. an entire galaxy, however small and faint, floating in the abyss between two giants, discovered recently enough that it has not yet made it into most published catalogues. These dwarf systems are real structures, real galaxies in their own right, containing anywhere from a few million to a few billion stars each. But placed against the void they inhabit, they are specks of foam on the surface of an ocean that has no far shore visible to any instrument we possess. Now lay the rungs of the ladder beside each other and look at the pattern. Earth to the moon, 1¼ light seconds, a distance humans have physically crossed. Earth to the sun, 8 light minutes, a distance we have sent probes near but never reached. Sun to the outer edge of the solar system, 1 to 2 light years, a distance no probe has yet crossed even a fraction of after 50 years of travel. Sun to the nearest star, 4¼ light years, a distance requiring thousands of years with our fastest technology. Width of the Milky Way, 100,000 light years, a distance requiring hundreds of millions of years with our fastest technology. Milky Way to Andromeda, 2.5 million light years, 25 times the entire width of the galaxy, a distance requiring billions of years at our fastest speed. Look at what happens between those rungs. Each jump is not an increment. Each jump is a multiplication so severe it renders the previous rung negligible. From Earth to the nearest star, the distance grows by approximately 270,000 times relative to the Earth-Sun distance. From the nearest star to the far edge of the galaxy, it grows by more than 20,000 times again. From the width of the galaxy to the distance of Andromeda, it multiplies by another factor of 25. Every rung destroys the one below it. Every scale you master becomes irrelevant at the next level. And notice where the most important conceptual break occurs. It is not between the solar system and the nearest star, though that jump is already staggering. It is not between the nearest star and the far side of the galaxy, though that jump is worse. The most fundamental break is between anything inside a galaxy and anything outside one. Within a galaxy, however enormous the distances, you are still moving through a populated space. Every few light years, another star. Every few hundred light years, denser stellar regions, star-forming clouds, clusters. The galaxy has internal structure you can navigate by. It has a coherent identity as a single gravitational system. Between galaxies, that coherence ends. The intergalactic void is not a bigger version of interstellar space. It is a different environment entirely. Interstellar space is the space between rooms in a very large building. Intergalactic space is the ocean between continents. Both can be measured in the same units. They are not the same thing. And treating them as the same thing, scaling up interstellar travel concepts to imagine intergalactic voyages, is the kind of category error that makes the problem seem smaller than it is. Andromeda sits at the top of this particular ladder. The most distant rung before the structure disappears into a darkness that has no visible upper limit. And we have not yet confronted the number in its most visceral form. We have worked in light years and miles. We have compared distances to solar system journeys and galactic widths, but we have not yet asked the question that turns the number from a measurement into something that actually lands in the body. We have not yet asked how long, not how far, how long, because distance is abstract, time is not. Time is the one currency every living thing understands instinctively, because every living thing has been spending it from the moment it came into existence. And when you convert 2.5 million light years into time, the number stops being a statistic and becomes something considerably harder to set aside. That conversion is what comes next, and when it arrives, the ladder does not simply reach beyond your grasp. It vanishes into a darkness so complete that you cannot see where the next rung might be, even if one existed. Numbers lose their grip on the mind when they grow large enough. The human brain evolved in an environment where the quantities that mattered were small enough to see and count. A handful of fruit, a group of animals, the distance to the river, perhaps a few thousand, if you were counting days or members of a community. Beyond that threshold, numbers become abstractions. They float through the mind without attaching to anything real. without producing any sensation that corresponds to their actual magnitude. You can say 2.5 million light-years. You can write it down. You can perform arithmetic with it, but you cannot feel it. It passes through cognition the way water passes through an open hand, leaving almost nothing behind. So stop treating it as a number. Turn it into time instead. Time is the one dimension of reality that every human being processes directly and personally. Time is birthdays and funerals. Time is the gap between planting and harvest, between childhood and old age, between the first breath and the last. Time is the medium in which every human experience occurs, and every human being has an instinctive, visceral relationship with its passage that no abstract number can replicate. When you convert the distance to Andromeda into time, the quantity stops being a statistic. It becomes something you can actually feel pressing against you. Begin with the fastest object humanity has ever built. The Parker Solar Probe, at its closest solar approach in December of 2024, reached a velocity of approximately 430,000 miles per hour. That is roughly 120 miles every second. At that speed, you could circle the entire circumference of the Earth in under 3.5 minutes. You could reach the Moon in about 33 minutes. You could cross from the surface of the Earth to the surface of Mars at its closest approach in roughly 3.5 days. This is not a theoretical figure. It is not a projection or a design target. It is a real velocity achieved by a real machine, built with real materials, guided by real mathematics, funded by real institutions, launched from a real launch pad on a real morning by real human beings who understood exactly what they were doing. It is the absolute pinnacle of our species' demonstrated ability to make a physical object move through space. Now pointed at Andromeda, 2.5 million light-years, 14.5 quintillion miles. At 430,000 miles per hour, the Parker Solar Probe would require approximately 3.9 billion years to complete the crossing. Call it 4 billion years, rounded for clarity. 4 billion years. The mind refuses this number on the first pass. It bounces off the surface of comprehension without penetrating. So let us give it something to attach to. The Earth itself is approximately 4.5 billion years old. The solar system condensed from a rotating disk of gas and dust roughly 4.6 billion years ago. Our planet solidified, developed a crust, accumulated oceans, and began the long, slow process of generating the conditions for life within that time frame. 4.5 billion years is the entire lifespan of our world, from formless cloud to the planet you are standing on tonight. A Parker Solar Probe launched at the moment Earth solidified from its primordial disk would still not have reached Andromeda today. It would still be somewhere in the intergalactic void. Approximately 500 million years of travel remaining before arrival. Every geological epoch in Earth's history, every mass extinction event, every ice age, every continental drift, every evolutionary transition from the first self-replicating molecules to the complex ecosystems that eventually produced the engineers who built the probe in the first place, all of that would have elapsed during the crossing, and the probe would not yet be there. That is what 430,000 miles per hour means against a distance of 2.5 million light-years. Now try a different speed. Not an engineering achievement, but a theoretical one. Suppose humanity develops propulsion technology genuinely far beyond anything currently conceivable. Suppose we build a spacecraft capable of sustaining 1% of the speed of light. 1%. That is approximately 6.7 million miles per hour, roughly 15 times faster than the Parker Solar Probe's peak velocity. No existing technology comes remotely close to this figure for any mission carrying meaningful mass over interstellar distances, but physicists consider it at least theoretically conceivable using approaches like nuclear pulse propulsion or directed energy propulsion of a sufficiently large and sophisticated kind. At 1% of light speed, the journey to Andromeda takes 250 million years. 250 million years. 250 million years ago, the supercontinent Pangaea was just beginning to fracture along fault lines that would eventually produce the continents we recognize today. The first dinosaurs were only recently established on land. Mammals did not yet exist. The world was alien in almost every meaningful sense. If a civilization had somehow existed at that moment and launched a spacecraft toward Andromeda at 1% of light speed, it would be arriving approximately now at a destination where the receiving civilization, if one exists, would have no way to know who sent it, no means of interpreting any message it carried, no connection of any kind to the senders, who would themselves have been extinct for geological ages. Push the speed to 10% of light speed, 67 million miles per hour. A velocity so extreme that the kinetic energy of even a modest spacecraft traveling at that speed would be measured in units comparable to nuclear weapons detonations per grain of interstellar dust encountered. The engineering obstacles are not merely large, they are likely insurmountable with any technology derivable from known physics. The energy requirements scale catastrophically. The collision hazard from microscopic particles in the interstellar medium becomes existential at those velocities. But ignore all of that. Assume the engineering is somehow solved. At 10% of light speed, the crossing to Andromeda takes 25 million years. 25 million years is the span separating the present day from the late Oligocene epoch, when the ancestors of modern great apes were just beginning to differentiate from earlier primate lineages. The entire evolutionary arc from those early primates to the species currently building spacecraft sits comfortably within the travel time to Andromeda at 10% of the cosmic speed limit. A journey of that duration does not belong in any category that the word travel can meaningfully occupy. It is not a voyage, it is a geological process. It is something that happens to planets, not to passengers. And even light itself, the absolute maximum velocity permitted by the universe, does not rescue the situation. It only reveals the depth of the problem in its most undiluted form. At exactly the speed of light, the crossing takes 2.5 million years, no less. The speed of light is not a speed that can be approached asymptotically until it becomes good enough. It is the hard ceiling of physical reality, enforced not by engineering limitations but by the mathematical structure of space-time. Nothing carrying mass can reach it. Nothing carrying information can exceed it. It is the final answer to every question about how fast, and its final answer here is 2.5 million years minimum, achievable by nothing that has ever existed or ever will exist within the framework of physics as we understand it. 2.5 million years. The mind needs something to do with that duration other than file it under very long time and move on. So let us walk backward through it. Let us stand at this present moment and step back through time, year by year in broad strokes, and see what we pass as we rewind through 2.5 million years of planetary history. Because every milestone we pass on that backward walk is a milestone that the light you see from Andromeda tonight has already outlived on its journey to your eye. 500 years ago, the Renaissance was reshaping European thought. Columbus had recently crossed the Atlantic. The printing press was proliferating across the continent. The light from Andromeda was already ancient beyond any meaningful description, but it still had 500 years of travel remaining. 1,000 years ago, the Viking Age was drawing toward its close. The Song dynasty governed China. The Islamic Golden Age was producing advances in mathematics, astronomy, and medicine that would shape European thought for centuries. The light continued crossing the void, indifferent. 2,000 years ago, the Roman Empire held the Mediterranean basin. Augustus had recently died. The infrastructure of roads and aqueducts that would define Western civilization for a millennium was being built. The light had 2 million years behind it, and still had 2,000 remaining. 5,000 years ago, the first cities were rising in Mesopotamia. Writing was being invented simultaneously in several independent locations. Recorded history was beginning. The light from Andromeda, already in transit for 2,495,000 years, had barely entered its final approach. 10,000 years ago, the last great ice age was releasing its grip on the northern hemisphere. Agriculture was being independently developed in the Fertile Crescent, in China, in the highlands of New Guinea. Human beings were learning for the first time to stay in one place, to cultivate rather than forage, to build structures meant to outlast a single season. The light had been traveling for 2,490,000 years, and still had 10,000 remaining. That residual distance, that final sliver, is the entire span of what we call civilization, and it was a rounding error. 50,000 years ago, anatomically modern humans were spreading across Eurasia. They were painting animals on cave walls with pigments ground from minerals, crafting figurines from mammoth ivory, sewing garments from animal hides with bone needles, crossing open water to reach islands that required deliberate navigation. The cognitive architecture that makes us human in any meaningful behavioral sense was already fully operational, and the light from Andromeda had 2,450,000 years behind it and 50,000 still to cross. The entire behavioral revolution that distinguishes modern humans from every earlier species fits inside the final 2% of that photon's journey. 300,000 years ago, the earliest known anatomically modern Homo sapiens appeared in what is now Morocco, at the site called Jebel Irhoud. These individuals were recognizably our species in skeletal structure, with brain cases broadly similar to ours, though the behavioral modernity associated with later populations had not yet fully emerged. The light from Andromeda had been traveling for 2,200,000 years when our species came into existence. We are not even a footnote in the duration of that crossing. We are a parenthetical remark inserted into the final entry of an encyclopedia that has been writing itself since before we existed. 700,000 years ago, Homo heidelbergensis, an archaic human species ancestral to both modern humans and the Neanderthals, was distributed across Africa and parts of Europe. There is evidence of controlled fire use, of wooden spears crafted with deliberate attention to balance and point geometry, of coordinated hunting strategies that imply a degree of social planning. Something approaching language was perhaps beginning to develop, though direct evidence for symbolic communication at this period remained scarce. The light had 1,800,000 years of travel behind it. 1.5 million years ago, Homo erectus was the dominant human species across much of the Old World. They had spread out of Africa into Asia and eventually into parts of southern Europe. They crafted Acheulean hand axes, teardrop-shaped stone tools ground to a symmetrical form that represents a genuine cognitive leap beyond earlier tool-making traditions. They almost certainly controlled fire. They hunted large animals cooperatively. They persisted as a recognizable species for nearly 2 million years, one of the longest runs of any species in our lineage, and they lived and died within the travel time of the light you see from Andromeda tonight. Homo erectus arose, diversified, spread across 2 continents, and went extinct before the photon that entered your eye this evening had completed its crossing. 2.5 million years ago, the genus Homo had only just emerged on the African continent. This is the moment. This is when the light you see tonight departed its source galaxy. The photons that constitute the soft silver glow of Andromeda in tonight's sky left their origin stars during the same narrow window of geological time in which the first members of our genus were picking up river cobbles on the East African savanna and discovering that striking them against each other produced edges sharp enough to cut. Not Homo sapiens, not any species recognizable as modern human. The earliest, most rudimentary precursors of the lineage that would eventually, after 2.5 million years of evolutionary experimentation, produce the species now standing under a dark sky looking up. The light is as old as our genus. It departed during the same geological moment that produced the first beings who could arguably be called the distant ancestors of human beings. Every species of Homo that has ever existed, from habilis to erectus to heidelbergensis to neanderthalensis to sapiens, every one of them lived their entire species' existence within the travel time of that light. The entire experiment of human evolution, from the first chipped stone to the last spacecraft, fits inside one photon's commute from a neighboring galaxy. That is what 2.5 million light-years feels like when translated into time. Not a number, a biological epoch. A span long enough for evolution to take a genus of clever African apes and produce, through countless generations of survival and death and reproduction, a species capable of building telescopes and measuring the distance across which that span of time had just been crossed. Now consider what this means for communication, not travel. just the act of sending a message. Suppose you encoded a signal, a radio transmission, a laser pulse, any carrier of information moving at the speed of light, and aimed it at Andromeda. The signal departs Earth. 2.5 million years pass. Assuming a civilization exists within Andromeda, capable of receiving and interpreting it, they compose a reply. They transmit it back at light speed. Another 2.5 million years pass. The reply arrives at Earth. Total elapsed time for a single exchange: 5 million years. 5 million years ago, the lineage leading to modern humans had only recently diverged from the lineage leading to chimpanzees. Our ancestors at that moment were early hominins, creatures walking upright some of the time and spending the rest in trees, with brains not substantially larger than those of modern great apes, and no evidence yet of stone tools, language, or any form of symbolic behavior. If a human civilization had somehow existed 5 million years ago and transmitted a greeting toward Andromeda, the reply arriving today would reach a planet populated by beings who share no language, no institutional memory, no cultural continuity, and arguably no species identity with whoever sent the original message. The civilization that composed the greeting would be as remote from the civilization receiving the reply as our earliest hominin ancestors are from a present-day physicist. A conversation with Andromeda is not merely impractical, it is incoherent as a concept. The timescale involved destroys the very definition of a conversation, because no entity on either end persists long enough to participate in both halves of the exchange. Communication at intergalactic distances is not a slow conversation. It is not a conversation at all. It is two monologues separated by an unbridgeable gap of time, each one speaking into a future so distant that nothing connecting the speaker to the listener survives the crossing. This is the dimension of the problem that raw distance consistently fails to convey. When you say 2.5 million light-years, it sounds like a fact about geometry, a measurement of space. But when you convert it to time, it becomes a fact about mortality, about the impermanence of species, about the terrifying brevity of everything we are and everything we have ever built relative to the gaps between the structures we inhabit. But there is one final calculation that deserves its own moment, because it approaches the problem from the opposite direction and reveals a different kind of horror entirely. Everything calculated so far has assumed traveling at speeds far below that of light. The results were measured in billions and hundreds of millions of years. Civilizations dissolved, species evolved and went extinct. Geological epochs elapsed. But what if we abandon any pretense of realism and ask the most generous possible question? What if we ask not how long the journey takes at achievable speeds, but how fast you would need to travel to complete it within a single human lifetime? Assume a generous lifespan of 80 years. To cross 2.5 million light-years in 80 years of experienced time, you would need to exploit a phenomenon permitted by special relativity: time dilation. As an object accelerates toward the speed of light, time aboard that object passes more slowly relative to time in the outside universe. At velocities sufficiently close to light speed, the difference becomes extreme. A traveler moving at 99.99999% of the speed of light would experience only a small fraction of the time elapsed in the external universe during their journey. In principle, if you could accelerate continuously at a rate comparable to Earth's gravity, 1g, you could reach velocities arbitrarily close to light speed, and the journey to Andromeda could, from your perspective, compress to a duration you might survive. The physics permits this, in principle. The known laws of the universe do not explicitly forbid it, but the energy requirements are beyond anything human civilization can currently approach. Accelerating even a modest spacecraft to the velocities required would demand more energy than our entire civilization currently produces across centuries of operation. And the practical obstacles: radiation exposure, microparticle collisions at near-light velocities, the engineering of continuous acceleration over decades of ship time, are so severe that no serious engineering proposal has ever addressed them in any form that resembles a credible pathway. Set all of that aside. Assume the engineering is somehow impossibly solved. You board the spacecraft, you accelerate, time aboard the ship compresses relative to external time, 80 years pass for you. You arrive at Andromeda, and when you step outside, 2.5 million years have elapsed back home. Earth has aged by a span longer than the entire existence of your genus. Everyone you knew is not merely dead. They are fossilized, their bones compressed into rock strata, their civilizations ground into sediment, their languages dissolved into silence. Every city you remember has been erased by ice ages and tectonic movement. Every nation you knew has been gone for longer than recorded history had even begun when you launched. The species that built your spacecraft may have evolved into something unrecognizable, or gone extinct entirely, or been succeeded by lineages that preserve no memory of ever having sent a ship toward Andromeda. You carry in your living memory a world that exists nowhere else in the universe. A ghost civilization, preserved in one skull, arriving at the shore of an alien galaxy with nothing behind it but extinction and nothing ahead but the unknown. Arrival at Andromeda under those conditions would not be a triumph. It would be the loneliest moment in the history of consciousness. A single mind standing at the edge of a trillion-star galaxy with the knowledge that everything it came from has been dead for geological ages and nothing is left to tell. Even the most exotic physics does not resolve this. Time dilation can compress the traveler's experience of the crossing, but it cannot compress the crossing itself. The 2.5 million light-years remain real. The void remains real. The photons still require 2.5 million years to make the trip, and any physical object must do at least as poorly. The universe does not offer shortcuts. It offers only the hard geometry of distance and the hard arithmetic of speed, and both of them, from every direction of approach, return the same verdict. Andromeda is beyond reach. Not beyond reach in the way that the deep ocean was beyond reach before submarines, or the moon was beyond reach before rockets. Those were engineering problems, waiting for solutions that eventually arrived. This is a physics problem. The distance to Andromeda is written into the fabric of space-time itself, enforced by the speed of light, which is not a barrier waiting to be broken, but a fundamental property of the universe in which we exist. And no technology that operates within the known laws of physics can overcome it in any time frame that preserves the identity, continuity, or relevance of the civilization that attempted the crossing. The nearest major galaxy, the one we call next door, and it has been out of reach since the moment the universe placed it there. There is a particular cruelty embedded in the way the universe has arranged this situation, and it only becomes visible when you hold two facts simultaneously in your mind. The first fact: we know Andromeda in extraordinary detail. We have studied it for over 1,000 years. We have photographed it with instruments capable of resolving individual stars across a gap of 2.5 million light-years. We have measured the rotation of its disk, mapped the distribution of its stellar populations, reconstructed its merger history, determined the mass of its central black hole, and modeled the chemical evolution of its spiral arms across billions of years of cosmic time. The panchromatic Hubble Andromeda Treasury Program, completed in January of 2025, produced a 2 billion pixel mosaic, resolving more than 200 million individual stars across the galaxy's face. We have catalogs, we have spectra, we have velocity maps, we have age distributions for stellar populations distributed across the full extent of the disk. We know Andromeda more thoroughly than we know the floor of our own oceans. The second fact: the distance separating us from Andromeda would consume 4 billion years of travel at our fastest speed. No signal sent toward it today will receive a reply within any time frame meaningful to any civilization currently in existence. No physical object built by human hands can cross the void between us and that galaxy within any duration that preserves the identity or continuity of the species that launched it. These two facts coexist without contradiction, and their coexistence is the thing that makes the distance to Andromeda something more than merely large. It makes it a statement about the fundamental architecture of the relationship between mind and cosmos. The universe permits knowledge. It does not permit access. And it maintains that distinction with a precision that feels, if you stare at it long enough, almost deliberate. Knowledge and access are not the same thing. This seems obvious when stated plainly. Knowing that a mountain exists is not the same as standing on its summit. Understanding the chemistry of a distant star is not the same as feeling its warmth, but in ordinary human experience, knowledge and access are tightly coupled. If you know enough about something to describe it in detail, you generally also have some plausible pathway toward reaching it, interacting with it, verifying your knowledge against direct experience. The gap between knowing and touching is usually a question of effort and resources, not physics. Andromeda breaks that coupling completely. The more we learn about Andromeda, the more real it becomes. And the more real it becomes, the sharper the edge of its inaccessibility. Every new image, every spectroscopic measurement, every refined model of its internal dynamics deepens our knowledge and simultaneously deepens the paradox, because knowledge without access is not the same as connection. It is a more sophisticated form of separation. You are not estranged from Andromeda by ignorance. You are estranged from it by space-time itself. And space-time is not an obstacle that additional knowledge can overcome. The most recent science sharpens this paradox rather than softening it. In January of 2025, the completion of the panchromatic Hubble Andromeda Treasury Program and its southern extension represented the culmination of more than a decade of coordinated observation. Over 600 individual Hubble pointings, accumulated across more than 1,000 orbital passes, were assembled into a single continuous panoramic image of Andromeda's disk. The resulting mosaic contains approximately 2 billion pixels and resolves more than 200 million individual stars, each one identified, catalogued, and characterized by stellar type, luminosity, and evolutionary stage. Astronomers use this data to reconstruct Andromeda's star formation history with unprecedented precision. The distribution of stellar ages across the disk reveals that Andromeda experienced a major merger with a substantial companion galaxy, approximately 2 billion years ago. The evidence is written into the galaxy's structure in multiple ways. There are coherent streams of stars in Andromeda's halo, debris trails from smaller galaxies consumed over billions of years. There are stellar populations of particular ages concentrated in specific regions of the disk, signatures of star formation episodes triggered by gravitational interactions during past collisions. There is the giant southern stream, a prominent arc of stars extending far from Andromeda's main body, almost certainly the remnant of a large dwarf galaxy disrupted and absorbed within the last few billion years. Andromeda has a violent history. It is not the serene pinwheel of popular imagination. It is a survivor of repeated gravitational encounters. Its current structure, shaped as much by what it has absorbed and disrupted as by any orderly process of internal evolution. And we can read that history in the distribution of light across its face, in the velocities of individual stars measured by spectroscopic instruments at observatories on Earth and in orbit. This level of detail is astonishing by any standard. We are reconstructing the biographical history of a galaxy 2.5 million light-years away, star by star, epoch by epoch, from measurements taken by instruments on a planet whose entire technological civilization is less than 10,000 years old. And none of it brings us 1 inch closer to setting foot there. Meanwhile, the very question of whether Andromeda and the Milky Way will one day physically merge has itself become scientifically contested in ways that illuminate just how extreme the distances and timescales involved truly are. For decades, the collision was treated as a settled conclusion. The two galaxies are gravitationally bound and approaching each other at roughly 110 kilometers per second. Early simulations suggested a direct collision and eventual merger in approximately 4 to 5 billion years, producing a large elliptical galaxy from the wreckage of the two spirals. This scenario was widely reported, carefully modeled, and represented in visualizations showing the two disks interpenetrating in slow gravitational catastrophe. Then the data became more precise, and the certainty began to dissolve. A 2025 study led by Sangmo Tony Sohn and colleagues, drawing on proper motion measurements from the Hubble Space Telescope and the Gaia Space Observatory, and incorporating the gravitational influence of the Large Magellanic Cloud, which orbits the Milky Way with roughly 15% of our galaxy's mass and exerts a significant perpendicular gravitational pull on our trajectory, found that the probability of a direct merger within the next 10 billion years may be closer to 50% than to certainty. The Large Magellanic Cloud's influence, previously underestimated in earlier simulations, could deflect the Milky Way's trajectory enough to convert what was expected to be a head-on collision into a glancing encounter or a series of passes that might not result in full coalescence for far longer than originally projected. A subsequent 2026 study by Wu and collaborators, using updated Gaia proper motion measurements for stars in Andromeda's outer halo to refine the galaxy's transverse velocity, pushed the merger probability back upward to approximately 90% over 10 billion years, with a median merger time of roughly 6 to 12 billion years from now. Further Gaia data releases expected in mid-2026 are anticipated to constrain the measurements further. The science remains genuinely unsettled. But notice what the debate itself reveals. Two galaxies separated by 2.5 million light-years, approaching each other at speeds of hundreds of thousands of miles per hour, and astronomers cannot yet determine with confidence whether they will collide. Because the distances and timescales involved are so enormous that tiny uncertainties in velocity measurements, uncertainties of a few kilometers per second in a closing speed of 110, propagate into radically different outcomes when projected across billions of years of orbital dynamics. A measurement error smaller than the margin of uncertainty in most everyday physical quantities becomes the difference between a direct collision and a near miss when the timescale is long enough and the distance is large enough. The gap between Andromeda and the Milky Way is so vast that even gravity, the most patient and far-reaching force in nature, takes billions of years to close it. And the outcome of that closing remains, for now, a question mark. There is a temporal dimension to this separation that the spatial description alone fails to capture, and it deserves a moment of its own. When you look at Andromeda tonight, you are not seeing it as it is. You are seeing it as it was 2.5 million years ago. Every photon reaching your eye from that faint silver glow departed its source star in Andromeda during a geological era when the first members of our genus were learning to chip stone on the African savanna. The Andromeda that exists right now, at this precise moment in the universe's history, is invisible to us. The light currently leaving its stars will not arrive at Earth for another 2.5 million years. Long after every human being alive today has been dead for longer than civilization has existed. Long after whatever our species becomes in that interval, if it survives at all, has had time to rise and fall and be replaced by something we cannot predict. The Andromeda we know is a ghost image, a photograph taken 2.5 million years ago by the universe itself, developed over the course of that entire span, and delivered to your retina tonight. If an observer stationed within Andromeda aimed a sufficiently powerful telescope at Earth at this very moment, they would not see our cities or our satellites, or the pale blue dot of our civilization. They would see a planet populated by early members of the genus Homo, creatures just beginning to explore the possibilities of shaped stone as a technological medium. They would see no evidence of language, no evidence of art, no evidence of symbolic thought. They would see a world that has no idea it is being observed, no capacity to imagine that something is looking back across the void, and no means of knowing that 2.5 million years from now, the descendants of those stone chippers would be constructing instruments sensitive enough to resolve individual stars in the observer's home galaxy. The two galaxies are not merely separated by space, they are separated by time. The version of Andromeda we see, and the version that currently exists, are different objects, divided by a temporal gulf so wide that the entire evolutionary history of our species fits inside it. We are neighbors in the spatial sense of the word, and strangers in every temporal sense. The Andromeda we study is ancient. The Andromeda that breathes and burns and evolves through the present moment is unknown to us, and will remain unknown for longer than our species has existed. This temporal isolation compounds the spatial isolation in a way that makes the word neighbor almost unbearable in its inaccuracy. You do not merely live far from this neighbor, you live in a different era. The light bridge connecting you to Andromeda carries information in one direction only, from past to present, from there to here. And it delivers news that is 2.5 million years old by the time it arrives. Any response you send will arrive when the universe has aged by another 2.5 million years. You are not in contact with Andromeda. You are receiving a transmission from a time before your species existed, addressed to no one in particular, carrying no message except the simple fact of its own existence. And you are answering it with instruments that will deliver their reply to a future so remote it shares no continuity with the present. The distance to Andromeda is not a gap between two places. It is a gap between two times. And the two forms of separation reinforce each other into something that the word isolation cannot adequately describe. Knowledge without access, proximity without contact, visibility without reachability. These contradictions are not accidental features of the universe. They are structural properties of a cosmos in which light travels at a finite speed and galaxies are separated by distances that dwarf the speed of anything slower. The universe built this situation into its geometry from the beginning, and no amount of technological sophistication changes the underlying arithmetic. We are observers, permanently, irreversibly, constitutively observers. Not participants, not travelers, not explorers in any galactic sense. We are beings equipped with extraordinary instruments of perception, capable of gathering light from the edges of the observable universe and extracting from it precise information about the physical conditions in galaxies billions of light years away. We are, in the realm of knowledge, genuinely cosmic in our reach. We have earned the right to say that we understand the universe in meaningful and profound ways. But our experience of the universe is confined to one small corner of one ordinary galaxy, and the nearest large neighboring galaxy, the one we can see with our naked eyes on any clear night, the one we have studied in finer detail than any other object outside our own system, sits behind a barrier of distance so absolute that it makes every dream of intergalactic exploration a category error rather than an engineering challenge. A category error because the problem is not that we lack sufficiently fast spacecraft. The problem is that the distance to Andromeda is woven into the fabric of the universe itself, expressed in light years and enforced by the speed of light. And the speed of light is not a wall waiting to be climbed. It is a property of space-time. It is the rate at which causality propagates through the universe. It is the speed at which information travels between events, the speed at which gravity waves move, the speed at which every form of electromagnetic radiation crosses the void. It is not a technical limitation. It is a feature of reality at the most fundamental level we have yet found. And reality has placed Andromeda 2.5 million light-years away. Visible, knowable, photographed in extraordinary detail, and absolutely, permanently, physically beyond reach. The light tells you it is there. Everything else tells you it might as well not be. Here is the thing about Andromeda's distance that most accounts of it fail to make explicit. It is not the worst case. It is the best case. 2.5 million light-years is not an unusually large gap between galaxies. It is not an outlier, not a peculiarly wide stretch of void produced by some unusual arrangement of cosmic matter. It is not the distance to a remote and isolated galaxy sitting at the fringe of some inhospitable region of the universe. It is the shortest intergalactic distance available to us, the minimum, the floor of the problem. The nearest major galaxy in the observable universe sits behind a wall requiring 4 billion years of travel at our fastest speed, and that is the best possible version of this situation we will ever face. Every other major galaxy is farther, most of them enormously so. The Triangulum galaxy, the third largest member of our local group, sits approximately 2.7 million light-years away, slightly more distant than Andromeda, and contains roughly 40 billion stars, making it a modest spiral compared to the two giants of the group. Beyond the local group, the distances stop being multiples of Andromeda and start being multiples of multiples. The nearest major galaxy cluster, the Virgo cluster, lies approximately 54 million light-years from Earth. It contains over 1,300 individual galaxies, ranging from enormous ellipticals to modest spirals, to irregular systems in various stages of interaction and disruption. 54 million light-years. At the Parker Solar Probe's peak velocity, reaching the Virgo cluster would require approximately 85 billion years of continuous travel. The current age of the universe is approximately 13.8 billion years. A journey to the Virgo cluster at our fastest speed would take more than 6 times the entire current age of the cosmos. The Virgo cluster is not remote by cosmological standards. In the context of the observable universe, it is practically local. It anchors one end of the Virgo supercluster, a larger structure of which our own local group is a peripheral member, and that supercluster is itself a tendril of a vastly larger structure. In 2014, a team of astronomers led by Brent Tully at the University of Hawaii used the peculiar velocity flows of thousands of galaxies, the deviations in their motion produced by gravitational attraction toward dense regions, to map the boundaries of the supercluster containing our local group. The result was a structure they named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea spans approximately 500 million light-years and contains the mass of roughly 100 million billion suns distributed across more than 100,000 individual galaxies. Our local group sits near its outer edge, a small cluster at the periphery of a cosmic continent we had not known we inhabited until a decade ago. 500 million light-years. At the Parker Solar Probe's speed, crossing Laniakea from one side to the other would require approximately 780 billion years, 56 times the current age of the universe. If a spacecraft had launched at the moment of the Big Bang and traveled continuously at our fastest achieved speed in a straight line across Laniakea, it would have covered less than 2% of the distance by today. And Laniakea is one supercluster among many. The observable universe, the sphere of space from which light has had sufficient time to reach us since the Big Bang, extends approximately 46.5 billion light-years in every direction from Earth. Within that volume, current estimates place the total number of galaxies at roughly 2 trillion. 2 trillion individual galaxies, each one containing anywhere from a few billion to several trillion stars, distributed across a volume of space so vast that the number of light-years required to cross it would itself require scientific notation to write legibly. 2 trillion galaxies, and we can reach none of them. Not one, not the nearest, not the closest cluster, not the nearest supercluster. Every single one of those 2 trillion galaxies sits on the far side of a void, requiring travel times measured in billions or hundreds of billions or trillions of years. The observable universe is not a territory. It is a panorama, a view from a fixed point that cannot be changed by any physical means available to us or conceivably available to us within any framework of physics we currently possess. But the situation is not static, it is worsening. The universe is expanding. This has been known since Hubble's observation in 1929 that distant galaxies are receding from us at velocities proportional to their distances, a relationship now encoded in the Hubble constant. But expansion alone would not necessarily place galaxies permanently beyond reach. If the expansion was slowing down, decelerating under the influence of gravity, as the mutual attraction of all the matter in the universe gradually braked the outward motion of its contents, then, in principle, distant galaxies might remain reachable given sufficient time and sufficiently advanced propulsion. In 1998, 2 independent research teams studying the brightness of distant Type Ia supernovae, stellar explosions that serve as reliable distance markers because their intrinsic luminosity is well calibrated, made a discovery that rewrote the expected future of the cosmos. The distant supernovae were dimmer than they should have been if the universe's expansion was slowing. They were farther away than the models predicted. The expansion was not decelerating, it was accelerating. Something was pushing the universe outward with increasing force, overcoming the gravitational attraction that should have been pulling it back together. That something is called dark energy. It constitutes approximately 68% of the total energy content of the universe. Its physical nature remains one of the deepest unsolved problems in all of science. It may be a property of space-time itself, a vacuum energy inherent to empty space that drives the expansion forward. It may be a dynamic field that evolves over cosmic time. It may be something else entirely. What is certain is its effect. Dark energy is accelerating the expansion of the universe, and that acceleration has direct and irreversible consequences for the long-term accessibility of the cosmos. Within the local group, gravity is strong enough to resist this expansion. The Milky Way and Andromeda and their accompanying dwarf galaxies are gravitationally bound to each other, their mutual attraction sufficient to overcome the expansive pressure of dark energy at the scales involved. They will remain associated indefinitely, drawing together rather than apart. But beyond the local group, dark energy wins. Galaxies outside our gravitational family are being carried away from us by the expansion of space itself. And the farther away a galaxy is, the faster the expansion carries it, because the expansion operates on every increment of space between us and the galaxy simultaneously, and more increments of space means more total expansion. At a distance of approximately 14 billion light-years, the recession velocity caused by expansion reaches the speed of light. Galaxies beyond that threshold are receding from us faster than light can travel across the expanding space between us, not because they are physically moving through space at superluminal velocities, which special relativity forbids, but because the space between us and them is stretching at a rate that exceeds the speed at which light can cross it. Light we send toward those galaxies will never arrive. Light they emit toward us will never reach us. They have crossed what cosmologists call the cosmological event horizon, the boundary beyond which no causal contact between us and the external universe is possible, even in principle, even with signals moving at the maximum permitted speed, and every day, more galaxies cross that horizon. As the expansion accelerates, the event horizon contracts inward relative to our position, enclosing an ever smaller volume of space within which meaningful communication is theoretically possible. The number of galaxies we could in principle interact with, even setting aside every practical obstacle of travel time and technology, is shrinking, not growing. The accessible universe, even defined as generously as physics permits, is getting smaller with every passing year. The implications projected forward across cosmic time are staggering in their completeness. In approximately 100 billion years, every galaxy outside the local group will have receded beyond the cosmological event horizon. From that point forward, the sky will contain nothing but the merged remnant of the Milky Way and Andromeda and their associated dwarf companions, suspended in an apparently empty cosmos. The cosmic microwave background radiation, the faint thermal glow left over from the hot early universe, will have been stretched by expansion to wavelengths so long that no instrument could detect it. The evidence for the Big Bang, for cosmic expansion, for the existence of any galaxy beyond our own merged system, will have been physically erased from the observable sky. A civilization arising in that era would look outward and see nothing, no other galaxies, no background radiation, no redshifted light from distant structures. Nothing but their own island of stars floating in what would appear to be an infinite and perfectly empty darkness. They would have no way to discover that the universe had ever been anything other than that single galaxy surrounded by void. The knowledge we possess today, knowledge of 2 trillion galaxies, of a cosmos 93 billion light-years across, of a Big Bang 13.8 billion years in the past, would be physically inaccessible to them. Not hidden behind some barrier they might someday break through, not encrypted in a code they might someday decipher, gone, carried beyond the horizon by the expansion of space, leaving no trace retrievable by any measurement. The universe is not merely large, it is arranging itself to become unknowable. This future desolation matters for the story of Andromeda because it reveals something about the present moment that is easy to miss. We live in a cosmologically privileged era, not privileged in any anthropocentric sense, not because of anything special about human beings or our planet or our position in the galaxy, privileged in the purely physical sense that we happen to exist at a time when the universe is still young enough that its full structure remains visible. The 2 trillion galaxies we can currently detect represent the maximum accessible inventory of the cosmos. That inventory is already shrinking. Every billion years, more galaxies slip beyond the horizon. Every billion years, the universe becomes a lonelier place, not because anything is being destroyed, but because expansion is severing the causal connections between structures that were once, in principle, reachable. In this context, Andromeda is not merely our nearest galactic neighbor. It is something more specific and more final than that. It is the one major galaxy we will ever have any physical relationship with. Not because it is the only interesting galaxy in the cosmos, but because it is the only one close enough and gravitationally bound tightly enough to remain associated with us as the universe expands and the horizon contracts. Every other major galaxy will eventually be carried beyond reach by expansion. Andromeda will not. Andromeda will fall toward us instead. The merger of the Milky Way and Andromeda, whenever it occurs, under whatever timeline the most refined measurements ultimately establish, is therefore not merely a collision between two galaxies. It is a consolidation. The universe is, in its slow and impersonal way, handing us our permanent companion, and then, over the following billions of years, removing every other galaxy from the sky. What remains after the merger? The combined elliptical system that simulations have informally named Milkomeda will be our final and only home, not a temporary residence in a universe full of other possible destinations. A permanent one. A single island in an ocean that will, on cosmological timescales, become infinite in its emptiness. Andromeda is the last major galaxy, not the last one that exists, not the last one we can see tonight, but the last one that will remain within the gravitational reach of anything in our cosmic neighborhood as the universe ages and expands and the horizon closes inward. Every other structure in the observable universe is, on the timescale of cosmological expansion, already receding, already moving toward the horizon, already in the process of being lost. We have one companion, 2.5 million light-years away, approaching at 110 kilometers per second, billions of years from any meaningful interaction, and that is the entirety of our cosmic inheritance. Consider the large-scale structure of the universe itself, because it reframes the isolation in one final way that deserves to be felt directly. The universe is not arranged uniformly. Matter in the cosmos is distributed in a pattern that astronomers call the cosmic web, a vast three-dimensional network of filaments, sheets, and nodes connected by threads of dark matter and ordinary matter, strung across enormous distances. Galaxies and galaxy clusters are concentrated along the filaments and at the nodes where filaments intersect. Between the filaments lie the cosmic voids, regions of space dramatically underdense relative to the average, stretching hundreds of millions of light-years across and containing almost no galaxies at all. The Boötes void, one of the largest known underdense regions in the local universe, spans approximately 330 million light-years. If you were placed at the center of it, the nearest galaxy in any direction would be hundreds of millions of light-years away. The entire observable sky would appear essentially empty, not dark in the way our sky is dark, punctuated by stars and the faint smudges of nearby galaxies, dark in a more absolute sense. A darkness without structure, without variation, without any point of light, bright enough to see with any instrument we currently possess. These voids are not rare anomalies. They constitute the majority of the universe's volume. The filaments and sheets and clusters where galaxies concentrate are the exception in terms of spatial occupancy, threading through a cosmos that is, by volume, overwhelmingly empty. The universe is less like a city full of buildings and more like an enormous dark ocean crossed by a few faint threads of foam on its surface. We happen to live on one of those threads. The Laniakea supercluster, with its 100,000 galaxies, represents a relatively dense region of the cosmic web. And even within that relatively dense region, the distances between individual galaxies are measured in millions of light-years. Even in one of the more populated neighborhoods of the universe, the isolation is absolute by any scale that life can experience. The local group, our own small cluster, spans roughly 10 million light-years and contains approximately 100 known galaxies, the overwhelming majority of them small dwarf systems containing a few million or a few billion stars. The two dominant members are the Milky Way and Andromeda. They account for the vast majority of the group's total mass and essentially all of its large-scale gravitational organization. Everything else is a satellite, a companion, a small, irregular system orbiting one of the two giants, or drifting through the group's volume without strong gravitational attachment to either. Two mansions, surrounded by dozens of garden sheds, separated from each other by 2.5 million light-years of near-perfect vacuum, and surrounded on every side by distances that make the gap between the mansions look like the space between neighbors on the same street. This is the architecture of our existence, not a universe teeming with reachable destinations, not a cosmos arranged for exploration, not a space that rewards ambition with access. A structure of extraordinary complexity and beauty, visible in its full depth from our vantage point, and separated from us by voids so wide and so empty that the act of crossing them would consume timescales beside which the entire history of life on Earth looks like a single afternoon. The distance to Andromeda is not an exception to this architecture. It is the most favorable expression of it. It is the architecture at its least severe, the void at its narrowest, the isolation at its most lenient, and it is already this extreme. Every other galaxy in the observable universe is a harder version of the same problem, and most of them are not harder by a factor of 2 or 5 or 10. They are harder by factors of thousands and millions, sitting behind voids so wide that the crossing would require travel times longer than the current age of the universe many times over, at speeds we have never achieved and may never achieve. The universe did not scatter its galaxies conveniently. It did not arrange them within comfortable reach of one another. It built its structures at scales that make intergalactic travel not a distant engineering challenge, but a physical impossibility, so complete that it barely registers as a question worth asking. And the nearest one is already this far away. That is the architecture. That is the structure. That is what the number 2.5 million light-years means when you place it in the context of everything that surrounds it on every side. But there is one more thing, one final dimension of this situation that has not yet been named directly, though it has been present in every paragraph since the beginning. And it is the dimension that turns this story from a description of astronomical distances into something that asks a question about consciousness itself, about what it means to be a mind embedded in a universe this large, capable of perceiving it in this much detail, and confined to a corner of it this small. That is where we go last. There is a moment in every childhood that astronomers and physicists tend to remember with unusual clarity. It happens outdoors, usually at night, usually young. You look up at the sky and something shifts. The stars stop being decorations and start being places. The darkness between them stops being absence and starts being space. Real space, traversable space, the kind of space that a sufficiently ambitious civilization might someday cross. The universe stops being a backdrop and becomes a destination, and in that moment something ignites that never quite goes out. A conviction that the cosmos is not merely large but reachable, not merely beautiful but explorable, not merely visible but, in some deep and eventual sense, ours. Every science fiction story ever written feeds that conviction. Every spacecraft in every narrative ever told about the future assumes it. Warp drives and hyperspace corridors and generation ships and stargates, the entire technological mythology of human expansion into the cosmos, rests on that childhood intuition that distance is a problem rather than a verdict, a barrier to be broken through rather than a boundary to be accepted. A chapter in a longer story that ends, eventually, with human consciousness spread across the galaxy and then across the universe, touching every world, inhabiting every corner of a cosmos that seems, from that early moment of wonder, to have been built for exactly that purpose. The distance to Andromeda does not challenge that intuition, it kills it, not by making the goal harder, not by pushing the timeline further into the future, not by requiring more advanced technology or more ambitious engineering or more generations of effort and sacrifice. It kills it by revealing that the goal itself belongs to the wrong category. That intergalactic travel is not a very difficult version of interplanetary travel, that the cosmos is not a larger version of the solar system, that the universe, in its actual structure, does not scale in the way the mythology assumes. The distance to Andromeda is not an engineering problem. It is a statement about the geometry of space-time, written in light years and enforced by the speed of light, which is not a record waiting to be broken but a fundamental property of the universe in which we exist. And that statement says something that cannot be argued away by optimism or dismissed by appeals to future technology or softened by the observation that humanity has surprised itself before. The nearest major galaxy requires 4 billion years of travel at our fastest achieved speed. That is not a challenge. That is a verdict. And yet the universe also did something extraordinary when it produced the conditions for consciousness to exist within it. It created a category of object capable of knowing it, not just inhabiting it, not just existing within it in the way a rock exists within it or a star exists within it, without awareness, without representation, without any internal model of the larger structure it is embedded in, but knowing it, measuring it, reconstructing its history from the patterns of light arriving after journeys of billions of years, inferring its future from the mathematics of gravity and expansion, holding its full scale, however incompletely and however inadequately, within the 3-pound organ sitting behind the face of a species that has been walking upright for only a few million years on a small rocky planet orbiting an unremarkable star. This is not a trivial achievement. Consider what it actually required. The universe had to expand and cool from its initial state into a configuration that permitted the formation of stars. Those stars had to live and die across billions of years, forging heavier elements in their cores and scattering them through space in stellar winds and supernova explosions. Those elements had to condense into second and third generation stars with planetary systems. On at least one of those planets, chemistry had to produce self-replicating molecules, and those molecules had to drive billions of years of evolution. And that evolution had to produce nervous systems, and those nervous systems had to become complex enough to generate awareness, and that awareness had to develop language and mathematics, and the ability to encode knowledge across generations. And all of that accumulated knowledge had to eventually produce telescopes and detectors and computational tools sophisticated enough to resolve individual stars in a galaxy 2.5 million light-years away. 13.8 billion years of cosmic history, from the Big Bang to the Hubble Space Telescope, from the first quantum fluctuations in the primordial plasma to the 2 billion pixel mosaic of Andromeda completed in January of 2025. All of it required, every step necessary. Remove any one of them and the knowing does not happen. The universe spent 13 billion years building the conditions for something capable of understanding it. And what it produced was a species confined to one planet, able to see 2 trillion galaxies, and able to reach none of them. That is not a failure. It is a specification. It is what consciousness looks like when it arises within the architecture of a cosmos built at these scales. Not a traveler, an observer, not an inhabitant of the universe in any expansive sense, a witness to it, permanently local in its physical reach, genuinely cosmic in its perceptual range, able to hold the full structure of reality within its awareness while remaining physically anchored to a single point within it. There is a philosophical tradition that finds in this situation a cause for despair. The universe is so large and we are so small, and the smallness seems in that reading to diminish us, to render our existence negligible, to make the whole project of consciousness seem like an afterthought in a cosmos that operates at scales where nothing we do or build or think or feel registers as anything but noise. But that reading gets the direction of the argument backwards. The universe's scale does not diminish consciousness. It reveals its improbability. The fact that something capable of measuring intergalactic distances exists at all, within a universe that had no obligation to produce it, within a cosmos that operated for billions of years with complete indifference to whether anything aware ever arose within it, is not a reason for despair. It is the most astonishing fact in the inventory of known facts, more astonishing than the 2 trillion galaxies. more astonishing than the 93 billion light-year span of the observable universe, more astonishing than the dark energy accelerating the expansion or the dark matter sculpting the large-scale structure, or the four fundamental forces that conspired across 13 billion years to produce the conditions for this particular conversation. The astonishing thing is not the size. The astonishing thing is that something small enough to fit on a rocky planet in an outer spiral arm can know the size. Go outside tonight. Find Cassiopeia, the crooked W in the northern sky. Let your eyes adjust until the darkness feels complete. Then look slightly downward and to the right, toward the place where the light is waiting for you. You will see a faint smudge, a pale wisp of ancient luminescence pressed against the black. Understated, easy to miss, easy to dismiss as nothing worth pausing for. But you know what it is now. You know what it has taken to reach you. Those photons departed 1 trillion stars during the same narrow window of geological time in which the first members of your genus were learning to shape stone into edges on the African savanna. They crossed 2.5 million light-years of near-perfect vacuum, passing through an intergalactic medium emptier than any vacuum human technology has ever produced, traversing a void in which the nearest star in any direction would have been an entire galaxy away, traveling at the only speed the universe permits for the crossing of such distances. For 2.5 million years without pause, without deviation, without any interaction that could slow them or alter their course, they passed through the outer halo of our galaxy. They threaded between the stars of the Milky Way's outer spiral arm. They crossed the final few light years of interstellar space. They entered Earth's atmosphere. They traveled the last fraction of a second of a 2.5 million year journey, and they arrived at your retina on this night while you stood under an open sky and looked up. The journey those photons completed is longer than the entire evolutionary history of your species. The galaxy that sent them is separated from you by a void so wide that traveling across it at our fastest speed would consume nearly the entire lifespan of the Earth. The nearest major galaxy, the one we call next door, the best case, the shortest impossible distance. And it is right there, visible with your naked eye, soft and silver and ancient and present, simultaneously the most distant thing you will ever see without any instrument, and the most inaccessible structure in the observable universe relative to anything that could be called next door. It gives you its light freely. It withholds everything else absolutely. It lets you look for as long as you wish, and offers nothing that could become a path toward it. This is what the universe is. Not a space to be explored in any galactic sense. Not a territory waiting for travelers ambitious enough to attempt it. A structure of incomprehensible scale and beauty, arranged at distances that ensure observation is the only relationship consciousness will ever have with most of it. A cosmos that spent 13 billion years producing the conditions for something capable of knowing it, and then placed that something in a corner of it so small that the corner itself rounds to zero against the full extent of what can be seen. You are standing on a rock orbiting a star in a galaxy containing 400 billion other stars, looking across 2.5 million light-years of intergalactic void at another galaxy burning with 1 trillion suns, and you can see it with your naked eye, and you will never touch it, and it is the closest one, and everything beyond it is farther, most of it incomparably so, and the universe is expanding and accelerating, and the horizon is contracting, and eventually, even the light from beyond our local group will stop arriving, and the sky will empty of everything except the one companion we have, the one galaxy close enough and bound tightly enough to remain, Andromeda, 2.5 million light-years away, approaching at 110 kilometers per second, billions of years from any collision, our nearest neighbor, our last neighbor, the only major galaxy that the long mathematics of gravity and expansion will leave within our cosmic reach as the universe ages into its final chapters. There is something in that fact that resists the category of tragedy, even as it resists the category of comfort. It is simply what is true. The universe built galaxies and placed them at these distances. It built dark energy and set it to work expanding the space between them. It built the speed of light and made it the absolute ceiling of physical travel. And then, within all of those constraints, it produced something capable of measuring every one of those distances, calculating every one of those travel times, understanding every one of those limits, and standing under a clear autumn sky to look at the results with something that might be called awe, or grief, or wonder, or simply the particular quality of attention that arises when a mind finally understands its own position in the structure it inhabits. You are small, the universe is large. The distances between its structures are so extreme that they transform the meanings of words like near and journey and neighbor into something unrecognizable from their ordinary usage. You will never cross those distances. Neither will anything you build or anything that descends from you through any number of generations. The cosmos is not a space designed for crossing. It is a space designed, if it was designed at all, for looking. And you are looking right now, tonight, standing on a planet that took 4.5 billion years to produce you, in a galaxy that took 10 billion years to build itself, in a universe that has been expanding since before time had the meaning it carries now, looking across 2.5 million light years at 1 trillion stars that have been burning since before your genus existed, receiving their ancient light in your eyes, understanding what it is and where it came from, and what it means that it is here at all. That is not nothing. That is, in fact, the most extraordinary thing in the observable universe. Not the galaxies, not the voids, not the dark energy, or the cosmic web, or the 2 trillion islands of stars arrayed across 93 billion light-years of expanding space. The fact that any of it is known, the fact that the light from Andromeda does not simply arrive and disperse into darkness, as it has been doing across 2.5 million years of crossing, but arrives instead at something that recognizes it, measures it, traces it back to its source, and understands, with whatever mixture of humility and wonder the situation demands, exactly how far it has come. A single candle does not illuminate the void between galaxies, but it is enough to see by. And on this night, on this world, in this brief and improbable interval of cosmic time in which the universe contains something capable of looking back at itself, the light from Andromeda is here, ancient, unreachable, beautiful, and ours, for exactly as long as we are here to receive it.